Hello, I'm Dr. Alison Griffiths of Staffordshire University. Contact details are given here, and today I'm going to talk about multi-user CDMA systems and multi-user detection. I'm going to show how we can send an original signal across a shared channel with lots and lots of other users. We're going to spread that signal so it's nice and wide, as shown here. We have other users in this sending information in through this channel. And there will also be some narrowband interference, and I will show how we will recover this signal back again. So, an overview of what I'm going to talk about. What is multi-user detection and CDMA? What are the different types of codes that we can use in code division multiple access? How we spread and despread the message, an example will be given. And then at the receiver, once we receive all our information, how we can recover that information using different types of detectors such as match filter decorrelator, and match filter minimum mean squared error. So, mobile communication systems. How do we get to 3G? There were two major migration paths. Essentially, everyone had the idea of mobile communications at the same time, except the different countries throughout the globe didn't speak to each other. So what happened was we had multiple systems that were completely incompatible. These are the major paths. So in first generation occurred in the 1980s in Europe. There are extended total access communication systems, or ETACs, and there were several versions of these. And in the States it was advanced mobile phone system. These were analog communications, because at that time we used analog, and it was based on frequency division multiple access, in which time each user had a shared amount of space along the frequency channel. So if I use this graph here, if this is frequency, then we would split the channel up into smaller bands, so there would be a lot of wastage because we needed some overlap between, so some space between these bands, otherwise one user would interfere with one another. Hence the number of users, or K, is limited in frequency division multiple access schemes by the number of frequencies. Hence this wasn't a very popular system. Another reason why it wasn't very popular is it wasn't very secure, because essentially somebody could listen in to the particular frequency and they could hear the message being transmitted. So then we moved on to digital communications, which was the second generation, which occurred in the 1990s. This is when all the countries in Europe got together and developed the global system for mobile, or what we know as GSM. It is a TDMA system, so if this is the frequency axis and this is the time axis, what happened was we would split the channel up into, if we had pure TDMA, then every user could access the entire channel for specific periods of time. Then the number of users was limited by the number of channels that we could have, because obviously if we waited too long, then we would experience delays, because we would have to wait too long for our next slot to occur. So what we could do is we could have a mixture of TDMA and FDMA, which is essentially what GSM was based on. So we're split up in different frequencies for different times, and we could hop between different frequencies at different times at some predefined manner. This makes it more secure. Again, in the US, there's also a TDMA counterpart, which is known as IS-54. This was not compatible with GSM, and also at the same time, then in the US, IS-95 was being developed. So IS-95 is the first instance of CDMA. In CDMA, each user is given a separate code which is orthogonal to one another. We will show what orthogonality is. What it means is if I get given a code and I transmit my data using that code, then unless somebody knows that particular code, my data will appear as noise to them. Hence, it's very, very secure. We could also swap codes at a predetermined time. As long as the transmitter and the receiver knows this information, then what was transmitted can be successfully recovered. Again, in the US we had wideband CDMA, and in the UK, in Europe we had wideband CDMA, and the US there's CDMA 2000. CDMA 2000 is backwardly compatible with IS-95, whereas wideband CDMA is backwardly compatible with second generation GSM. I haven't mentioned GPRS, which is General Packet Radio Service, and enhanced data rates for GSM evolution. The reason that they occurred, they are 2.5G, and they appeared because the licensing in Europe was so expensive that GSM needed to be future-proofed, because we couldn't throw, whenever we get to a new generation, we can't throw away the previous generations, because the users will be still using second generation handsets. Nobody uses first generation handsets anymore. So you'll notice in some areas you'll get 3G coverage. Then if you're a bit more in a remote area, you may get Edge or GPRS or just GSM. Hence the backward compatibility and the coverage. So this is where we are. So what about 4G? The reason that we're concentrating on 3G is that 4G is, the idea is still based on it. I'll just go back to 3G as well. The reason we can be backwardly compatible is due to the fact that we now have software-defined radios. So our handset can change its settings, change its connection type to the network based on its location. This is why we can also connect using Wi-Fi using a smartphone. So now 4G. 4G is aimed that we will have a peak speed of 100 megabits for high mobility users and 1 gigabits per second for low mobility users. These have been specified in March 2008 by the International Telecommunications Union Radio Unit, ITU-R, as IMT Advanced. There are two versions. There is long-term evolution, LTE Advanced, and also mobile WiMAX Release 2. So this will be used in the cellular, and this can be used in for the high speed link, which is more like a Wi-Fi and WiMAX. So IP telephony will be used, and orthogonal frequency division multiple access. If we think of code division multiple access that we're going to talk about now, if that is a serial communication, like a serial circuit, then OFDMA is each user's data can be transmitted in parallel. So we can either transmit multiple copies of the data if we don't want to make any errors, or we can transmit, say, bit 1 on channel 1, bit 2 on channel 2, bit 3 on channel 3. So this is how we can get the higher speeds. The other thing that we can have is we can have multiple antennas. So our mobile phone, rather than having a single antenna, can have multiple antennas. 5G, 5 generation, there's no particular specification that describes what 5G will be. There's nothing's been published by a standardization body. However, updated standards that define the capabilities beyond 4G are currently under consideration. These are going to be grouped under ITU-T 4G standards. I'm sure there will some 5G standards will soon emerge. So, what is CDMA? That's the next point. So CDMA is the multiple access technique in which many users share a single channel resource, code or power. The bandwidth in a CDMA system is very much greater than the minimum required bandwidth for the signal transmission. A pseudo noise or PN random signal converts the narrowband signal to a wide band noise-like signal. Now we're going to look at the different types of signals in a future slide. The original signal is multiplied by a very large bandwidth spreading code. So if we've got our narrowband signal, we multiply it by a very wide band code, which gives us a very wide band signal that we transmit. The PN has a much larger chip rate or frequency than the signal data rate. So what we're essentially doing is, if we have 1 bit of message, we're sending that, we're multiplying that by multiple chips for our code. We will go through this in the next few slides. Each user has got its own individual code, which is orthogonal or near orthogonal to all other PN codes. We'll look into this again. The receiver needs to know that code, or essentially it needs to know how it was transmitted, and it needs to be in synchronization with it. And it also, the power of all the users at the receiver determines how much noise there is after signal despreading and demodulation. It is therefore necessary to control the power of each user in order to avoid excessive interference. I'll just do this with a diagram now. So imagine if we have a base station or a node B here, and we have one user here, and we have one user here. Now, in traditional mobile phone systems, all users transmit at the same power. So this signal is travelling this distance, D1. I'm using this notation because this shows a radio signal, and this signal is travelling D2. Obviously, D2 is much less than D1, and the power, due to attenuation of the path, is going to be the received power at node B from the user 2, so P2, is going to be much greater than P1. Now, if we're trying to despread these signals, what's going to happen is the signal from user 1 is going to be drowned out by the signal from user 2. So ideally, the received power at the node B needs to be equal. So P2 needs to equal P1, or received power 1 needs to be equal to received power 2. So in this case, what happens is the node B will give instructions to a particular mobile to increase their power or decrease their power dependent on the received power. So the instruction to user 1 would be increase your power, and the instruction to user 2 would be to decrease your power. Now obviously these users do move because they're mobile nodes, so if user 2 decided to travel away from node B, so the distance is getting larger, node B would be telling that user to increase their transmission power, and consequently if user 1 was moving towards node B, then it would be told to reduce the transmission power. Obviously this is for transmission from U1. Node B would be transmitting downlink packets, because from user 1 to node B is uplink, from node B to user 1 is downlink. It would be transmitting those packets using the required power also. So what does the system model look like? Here we have the message, which is our 1s and -1s. And then we feed this to our transmitter. We then multiply our spreading code. We multiply it if it's in ones and minus ones, whereas if the input data is ones and zeros, then we use the exclusive OR. Exclusive OR and multiplication is the same thing. We use exclusive OR when we're using logic gates, whereas we use ones and minus ones when we're thinking in terms of voltages. We'll need to convert the 1 into, say, a 1 volt and a 0 into a minus 1 volt, or we do it the other way around. So that could either be a 1 could be determined by a minus 1 volt and a 0 is determined by a 1. It just depends. Well, the transmitter and the receiver both need to do it the same way around. So we multiply the message signal by the code, and then this gives us a spreaded signal, the increased bandwidth signal. We then pass that to the channel. If there was other users, then their spreading code, so P2 and say P3, would also be passed to the code to the channel. So this would be P1. So at the receiver, it would consist of our P1 of T, our spread code from message 1, and our spread code from the other users up to PK, and also the noise. So at the receiver, the received signal R of T is comprised of the message times the code plus any other users, P2 to PK, plus the noise. I'm going to assume that there's no other users here at this moment in time. So the D of T is we multiply the received signal by the same code, and then we should recover D of T. And then D of T should be almost equal to M of T, if we've done the operation right, with some errors. And those errors are dependent on the signal to noise ratio of the channel, which is equal to the signal power and the noise power. We will look at this relationship in more detail. So, if our message is comprised of ones and minus ones, as I mentioned before, in the time domain, so we've got 5 bits being transmitted here, then in the frequency domain, we have a square wave, so we have a very narrow band signal. So that's the bandwidth of our signal, our message. This is a bilateral spectrum, so it's essentially from 0 to there. So that's twice the bandwidth of the message. So our spreading code, in this case, we have 8 chips for 1 bit. That is repeated for every single bit here, 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 and here. So if we have a 1, essentially we multiply the 1 by when we have a 1 and we get a 1. When we have a minus 1 on our code, we multiply it by 1 and we get a minus 1. So essentially when we have a 1, we have a copy of the spreading code. When we have a minus 1, we have the inverse. Here we have a copy, here we have a copy, and here we have the inverse. In the frequency domain, we can see that because this is 8 times higher chip rate, then the bandwidth of our signal is much larger. The bandwidth is determined where we get to the first null, and again here that is 2. The bandwidth, twice the bandwidth of the spreading signal, or A. When we multiply the two together, the bandwidth of the resultant is actually slightly wider, but it's still 2BA. And then we will add noise to our signal. Now the noise only appears at those frequencies. So what does this look like? We have a narrowband, or BM, of the message bandwidth of the message signal. So this is the Fourier transform of the message signal, which is the capital M in terms of omega, or frequency. So and A is the signal, the spread sequence. BA is the bandwidth of the spread sequence, and when we multiply the two together, then P of the spread signal is given by P omega, and its bandwidth is greater than BA, so BA plus half of BM. Here we've got the power is message times spread signal, or the exclusive OR of message omega times A omega. So BA is much greater than BM. Then this is convolution, exclusive OR, sorry. BP is approximately equal to BA. This gives us the BP is the bandwidth of P. So that is approximately equal to BA. So we can say that this is sufficiently small that the gain, or the processing gain, is the bandwidth of the spread encode divided by the bandwidth of the message. So what's the ratio between the frequencies of the message signal and the spread encode? And that's the processing gain. So before spreading, we've got a narrowband signal, and then after spreading we have a wideband signal, and we also have the noise. The noise is determined by sigma squared, which is the variance of the noise power times the bandwidth of the message only. This is important, that it's only the bandwidth of the message. But the processing gain is BA over BM, as we've just shown. After spreading, the signal to noise ratio of our A is P divided by G sigma squared. But after despreading, the signal to noise ratio of our message now only occupies this frequency, so 0 to BM. So the signal to noise ratio of our message is equal to P divided by sigma squared, which is why sigma squared has the BM here. So we only get the noise from here to here, not from here to here. If the codes are all orthogonal to each other, the multiple access interference, or the interference supplied by other users, is 0, and therefore theoretically an infinite number of users can use the channel if the power at the receiver is the same. So we have the strict power control, as I already mentioned. So what does this look like? For multiple users, so we've got user 1 here and user 2 here, occupying the same bandwidth, just a different colour. They're shown in this graph as on top of each other because they're additive. However, when we despread the signal, the multiple access interference is just slightly higher because it looks like noise. And again, the noise is only effective at this bandwidth, not the entire bandwidth. So this is how we can have multiple channels travelling through the same channel if they are totally orthogonal, then this multiple access interference would not have any effect whatsoever. It would just be the same as the noise. So if we do this in terms of the equation, then the received signal R of t that we had before is comprised of M of t, A1 of t, M2 of t times A2 of t plus N of t. Now again, we could add more users here. The received signal is still R of t times A1 of t, however R of t has changed. So what we have is we have M1 of t, A1 of t times A1 of t, P2 of t, so the power of our second message, times A1 of t. So essentially P2 of t is A2t, M2t, A2t times A1t, plus noise, or the additive white Gaussian noise, times A of t. So the interference is given by P2 of t times A1 of t. The desired signal is A1 of t times A1 of t, and we will show that if we multiply two spreading codes together, because they're orthogonal, then we will get the identity matrix with a gain of the spreading gain. So essentially we will get gain M1 of t at the output. So if we divide by the gain, then that means we should recover the message. Previously we had a gain of 8. What this means is if one error was received, or one bit was received in error of those 8, then we would still get the correct results. If 2 bits were received in error, then 6 would still be correct, so we'd still get the correct result. If 3 bits were received in error, then 5 bits would be correct still, and we'd still get the correct error. However, if 4 errors were made, then we'd have 4 bits correct in error, 4 bits correct, so we would possibly not get the correct result. If 5 errors were made, we would get the wrong results, and so on and so forth until we get to the processing gain. This is why CDMA is so robust, because a number of errors can be made and we will still get the right result.